Hello friends, welcome to G-Centric. So we will continue with our questions. Question number 180, it says that the switch is open for long time and it is closed at t is equal to 0. So we have to find the generalized equation of current and voltage. Okay, so it is the switch is open for long time. So starting with our step 1, we have to analyze at t equal to 0 minus. So it says it's open for long time, so our circuit will be, this is 19 volts, this is 20 volt, and we have 60 ohm. Then this switch is open. So here we have got 70 ohm. And now this, when it is at t is equal to 0 minus, it is with source. Okay, so we will write it with source. Now this will be open. Sorry, this will be, inductor will be short. Okay, so inductor is short circuit. And this current flowing through this is IL of 0 minus. Okay, here also we can, since this is open, altogether it will be same current flowing in this one, that is IL of 0 minus. So we can find what is the IL of 0 minus using the KVL. Okay, so using the KVL, this is plus, this is plus. Okay, so 20 plus 19 is 39. 39 divided by 130. 39 over 130, which comes out to be 3 by 10 amperes, which is also true for IL of 0 plus. Okay, so we got our first expression. Since this is inductor, only we are going to find the current through the inductor. Now we will move on to the step 2, that is at step 2, t is equal to 0 plus. So at t is equal to 0, what is happening? The switch is getting closed. So we get a short circuit path over there, and our circuit will look somewhat like this. This is 19 volt, this is 20 volts, and here it is 60 ohm. This is short circuit, and inductor will be open with the amount of current, with a current source of 3 by 10 amperes. So 3 by 10 ampere, and here we have one more resistor, that is 70 ohm. So now we have to find VL of 0 plus. Okay, so this is the VL of 0 plus. What we have to know? We have to know the current in this one, and we have to know the voltage drop across this one. So since this is a short circuit path, the current in this will be flowing in this itself, and the current in this is, okay, same current will be flowing in this loop. This is one loop and this is another loop, because if you take similar one loop, there will be no return path for the current. So this is like self loop currents. Okay, so in this loop we know what is the current, that is 3 by 10. Okay, so here is 3 by 10. So when it is 3 by 10, then the voltage drop across this will be 17 to 3 over 10, which we will get it as 21 volts. So now we know here voltage, here also voltage is known, so we can easily find VL of 0 plus. So it is nothing but 20, apply KVL in this loop, minus 21, and you get minus VL of 0 plus equal to 0. So VL of 0 plus is nothing but minus 1 volt. Okay, next coming to step number 3. What we have to analyze? T equal to infinite. So at t is equal to infinite, still the switch is closed. Okay, and what will be, it is still with source, so hence the inductor will be short circuit. What we can write here, the equation or the circuit becomes, this is again 19 volts, 20 volts, this is 60 ohm, this is short circuit, and 70 ohm. Okay, this is short circuit. So this is IL of infinite. Okay, so this is 20 volts. We have to find IL of infinite. So this is with source. Now if it is with source, how do you find IL of infinite? We know already VL of infinite is 0. To find the IL of infinite, okay, we can apply KVL here. Okay, since this is like a short circuit path, everything will go in this way. Okay, if the current is there, this will be here, so this is into this we cannot take the consideration, but IL of infinite is here, so we can calculate it by KVL, 20 over 70. that is 2 by 7 amperes. Okay, so we have got all the initial and final values, but one is left, that is the time constant. So how do you calculate the time constant? This is RL circuit. Okay, so it will be L equivalent upon R equivalent. Okay, so now at steady state, time constant is calculated at steady state itself. So this will be the only circuit. We know what is the value of L, that is 1 by 3. To calculate R equivalent, how do you do? So if you see the current, everything will go into this short circuit. So when it is going into the short circuit, this will be not calculated. Okay, so only we have got 70 ohm as our R equivalent. So our time constant will be 1 over 210 seconds. So now how do you calculate the generalized equation? I'll write it over here. So generalized equation is nothing but for IL of t, final value, that is 2 by 7, then initial value we have to find, which is 3 by 10, then minus final value e to the power, time constant 1 by 2 over 10. So if it goes up, it will be 210 into t. Similarly with voltage, final value we have got 0, then initial value we have got minus 1 plus 0, and time constant is 210 t. Okay, so this is the analysis for the time transient analysis for this question. Okay, so we will see some more problem based on this. So coming to this question number 181, which was asked in GATE 2017 in electrical branch. Okay, so now the question is, the switch in the figure was closed for a long time. So they have given it was closed, it was not open, it was closed for a long time, but it is opened at t equal to 0. So the current in the inductor 2 Henry for t greater than or equal to 0 is, they have given this much option. So at the current through the inductor at 2 Henry, that means we have to form a generalized equation for IL of t. Okay, so with the specific values, now we have to solve for this one. Okay, just by analyzing the time constant. Okay, at t is equal to 0 minus 0 plus, it is not required. Okay, we will see why, and then t is equal to infinite. Okay, so we will start with our step 1, that is at t equal to 0 minus. So at t is equal to 0 minus, the switch was closed. Okay, since the switch was closed, the inductor is with source. Okay, so when it is with source, the inductor will be short circuit. So our diagram will be somewhat like this. This is plus minus 50 volt, 6 ohm, this is closed, 8 ohms, then again we have 8 ohm, then here is 32 ohms, here also we have 32, and the inductor will be short. So this is nothing but IL of 0 minus. Okay, so now if you see again, okay, so if you see this one, this is same node. Okay, when it is same node, what will happen here? This is 0 volt. Now this is again same potential, which is 0 volt. So when it is 0 volt, then it will be having irrelevant branches. Okay, this element also does not count, this element also does not count in the calculation. So now this is a short circuit path. So since we have to find the IL of 0 minus, we have to know what is the total current in the circuit. Okay, so once we know that, it is easy to get the IL of 0 minus. If we take this as current I, which is the total current, then this is like a resistor thing. Okay, we have got more resistors, so we can reduce this equivalent and we can get V by I. Okay, so now this 8 and 8 are in parallel, so it will be 8 plus 8 again half, 4 plus 6 is 10. So our total current I will be equal to V by R equivalent, which is 5 ampere. So 5 ampere of current is flowing in this one. Now this is 8 ohm, this is 8 ohm. Whatever current flows here, it will go in this IL of 0 minus, because these two branches we are not going to consider for the current calculation. Okay, so this is 8, then it will be 2.5 here, 2.5 here. Okay, so this will be nothing but 2.5 amperes, which is also equal to 0 plus. Okay, so now we have got already 0 plus, so there is no need to calculate for step 2, that is at t equal to 0 plus. We can directly jump to step 3 at t equal to infinite. Okay, so it says at t is equal to 0 the switch is open. Okay, so it will be a open circuit. Now how the inductor is like, when it is open it is without source. Okay, without source. When it is without source, it means that the energy is dissipating in it. Here itself everything will dissipate, hence IL of infinite will be equal to 0. So you do not need to draw the circuit also. So it is source free circuit. So now coming to the equation generalized, what will get IL of t, final value plus initial value is 2.5 minus final value. Okay, so we have to calculate now time constant. Okay, so how do you calculate the time constant? Tau. It is again RL circuit. So L equivalent by R equivalent. So L equivalent directly we know, we can divide this one. Okay, so this is dividing, we will get L equivalent which is 2 Henry, and for R equivalent, if you see, we have to analyze at t equal to infinite. So this is not there, 32 and 32 are in parallel. What is 32 by 2? 16, 16 plus 16, that is in parallel, 16 plus 8 is again 24, 24 plus 8 is 32. Okay, so that is 32, I will just check it here, they are in parallel. Okay, so 16 for 32, 16. So this L equivalent is 2 Henry divided by R equivalent. So we have to see it from here, 32, 32 parallel, so you will get it as 20, 16, 16 plus 8 is 24, 24 and 8 are in parallel again, so 24, 32, 4, then 6 ohms. Okay, so 6 ohms, we will write it here, which is again 1 by 3. Okay, so now I think it will be 4 ohm, 4 ohm. Okay, so this is 8. 2, 1, yeah, 1 by 4 seconds. So this will be our time constant. So when it is, when we have got the time constant 1 by 4, then it is nothing but t by tau. So tau is 1 by 4, when you replace it, it will go in the numerator, which we will get it as this one. So final expression for this inductor, current through the inductor is 2.5 e to the power minus 4t. Okay, so in the option we have got first one. So this is the correct option. Okay, so if you forget to write this as 1 by 4, if you take directly, then it will divide it by 4, then it will come as 0.25. Okay, so that should be, we have to be very careful with. Okay, so this is the gate question which was asked in 2017. Okay, so we will see some more problem based on this. So coming to question number 182. Okay, it's one of the good question which says we have to find I1 of t and IL of t for t greater than or equal to 0. So now here the voltage source is 100 u of t. So this type of problem we have already seen that when u of t, okay, so at t time is equal to 0, it will be 0 and 1 when t is greater than 0. Okay, so for our step 1, if they have given u of t, then what it will be? It is like 0. Okay, so it feels without source. Okay, at t equal to 0 minus, because it is negative, right? We are analyzing for the negative thing, so it is without source. So if it is without source, it means that we have dependent source also, but when independent source is not there, this dependent source will be inactive as well. So it is a dead circuit, so it will be without source. Okay, so when it is without source, it is initially relaxed. Okay, so initially relaxed. Our IL of 0 minus will be equal to 0, which is also equal to IL of 0 plus. Okay, now we have to go for step 2 because we have to calculate I1 of t. Okay, I1 of 0 plus as well as I1 of 0 minus. Now coming to the step 2, okay, we have even the dependent source introduced this time. So at step 2, t equal to 0 plus. Now the circuit is with source, okay, because we are analyzing for t greater than 0. So how it will behave? It will be open circuit at t is equal to 0 plus. Which will be open? Inductor will be open. Okay, so here we will write it here 100 u of t. Okay, we do not need to write u of t. So this is 10 ohms and here it is open. Next we have 20 ohm with plus minus 20 I1 of 0 plus. So here also it will be I1 of 0 plus. So it is very easy to calculate I1 of 0 plus. Apply KVL, 100 minus 30 I1 of 0 plus and minus 20 I1 of 0 plus equal to 0. Okay, so if it goes over that side, I1 of 0 plus will be 100 by 50, which is 2 amperes. Okay, so next coming to step 3. So at step 3 we have to analyze for t equal to infinite. So at infinite still it is with source. Okay, at steady state it is with source. So if it is with source, then inductor will be short circuit. So this is 100 and we have got 10 ohms. This is short circuit. So this current through this will be IL of infinite and here it will be 20 ohms. Okay, with plus minus 20 of, if this is I1 of infinite, this will be also I1 of infinite. Okay. Now this is, if we also substitute 2 into, it will be 200 amperes. Okay, so that is the current now. Now we have to find IL of infinite as well as I1 of infinite. So to find that, now if you take this as one node, and we can take using this nodal, we'll just keep this one as it is. Okay, this will be having the same potential. Okay, to find the IL of infinite, first we need current from here as well as current from here. Okay, once we know the current from here and here, we can easily calculate the current through the inductor at infinite. So now to do that, if you see this is at the same potential, so if this is at 0 volt, this will be also at 0 volt. Okay, so now this is higher potential, lower potential, so the current flows in from higher to lower. So this is 100 minus 0 divided by 10. Okay, so it will be 10 ampere. Similarly, you can find I1 of infinite from here to here, right? So it will be nothing but, so here we have got it as 10 ampere. Substitute this 10 in I1 of infinite, which will be 200 volt. Okay, so for the dependent source, this is the dependent source value I1 of infinite. So we have found out I1 of infinite value, that is nothing but 10. So this will be 200 volts. Once it is 200 volts, then you can easily apply the nodal 200 minus 0 divided by 20. So again this current, if we take it as some I of infinite, okay, we will take it as I of infinite. This will be again 10 ampere. Okay, so 10 ampere is coming from here, 10 ampere is coming from here, and the IL of infinite will be 20 amperes. Okay, so this is the question. Now we have to find the generalized equation. We have got I1 of infinite, IL of infinite, initial values, okay, of I1 and IL. So now one thing is left, that is the time constant. So a time constant is analyzed at t equal to infinite. Now this is an inseparable resistor also we cannot keep here, and this resistor inductor we cannot separate it. But we know this is L by R. So we know the value of L, that is 0.1 Henry. So we need to calculate for R. So there are two methods in this to calculate the R equivalent. Either we can put a voltage source, okay, take V by I ratio, or we can just short circuit this one, and we can use the Thevenin's method for calculating R equivalent. Okay, so here we will take our first method. We will introduce a voltage source here, okay, that is V, and the current through this is I. Okay, now once we know that, we can, I'll rub this one. Okay, so now we have here V, okay, so this is 100, we have I1 of 0 plus is 2 ampere, okay, this also I'll rub it, okay, we will take this as V, that is because there are only one voltage source is there in between the reference and non-reference node, so this appears here as V. Now we can take it, apply the nodal, 100 minus V divided by 10, okay, then we have got V over, sorry, we are going from this way, from V to 100, so we will take V minus 100 over 10 plus V, okay, so plus V. So now we can apply nodal. Before that we have to inactive our independent sources, okay, so this if I remove, okay, so this is here, this will be short circuit, okay, inactive the independent voltage source, short circuit, current source, open circuit. Okay, so now this is nothing but V, same potential, okay, whatever there is only one voltage source is present, so V will appear here. So it will be V over 10 plus V minus 20 I1 divided by 20 equal to incoming current, that is I, okay, so this is 10. Now we have two unknowns, so we have to take I1 also. What is I1? So this here is the I1, we can take it as V minus 0, so it will be minus V over 10, okay. So put this I in this equation, so we will get the V by I ratio, which is nothing but R equivalent, equal to 4 ohms, okay. Just put it over here, solve it, you will get V by I ratio, take it 4 ohms, okay. So put this 4 ohm over here, it will be 1 over 40 seconds. So I1 of t is nothing but final value, that is 10 ampere plus initial value 2 minus 10 divided into e power minus 1 by 40, so it will be 40 t. Similarly for IL of infinite, IL of t, final value is, what is the final value for this one? 20, initial is 0, minus 20, e to the power minus 40 t. Okay, so this is how you will solve the question. We will see some more problems based on this in the next lecture. Thank you.